Okay, so good afternoon. I'm going to give 3 talks. One today is like an introduction, and tomorrow one on shielding, like the basic ideas about radiation shielding. And then another one before Dr. Latke from Tufts University on radiobiology, radiation risk. My background is in nuclear physics, and then I moved into biophysics and radiation biology. And usually we're challenged because interdisciplinary is you're challenged like the physics point of view, talking to biologists, and biologists talking to the physicist part of the problem. So this will be different because it's mostly engineers here, I would imagine. So that's okay, you do. So that's good. Okay, so it's a little bit different, but not radiation. And I'm also, but it's typical. I'm also the vice president, to be the president-elect of the Radiation Research Society. So everyone should look into that. That's a good society to join. We have our meeting in Puerto Rico this year. Next year, New Orleans. We have to go to fun places, and that's very interdisciplinary with physics, biology, medicine, some engineering, and et cetera, with radiation risk and radiation oncology. So I always encourage people to join that. So I'm going to give a little background on the problem. The problem is a little bit different than what people might think, but maybe it's right on for others. So we have the NASA Space Radiation Program. This is a program the goal is to understand the risks of space radiation and to the astronauts look for ways to mitigate it. And so this is a chart. This is from a paper we did that was published in the Lancet Oncology. But you can see these are old pictures on the very far right from my side or left on your side of particles going through nuclear emulsion. So when the particles go through the emulsion, they ionize and then leave this density of grains. And you can see as you go up in the charge number from protons to iron, you can see it actually becomes like a microscopic or macroscopic phenomenon where just a single nucleus is able to give this very wide track. And then these green foci are a more recent way in the last 5 to 10 years of looking at this, where the fluorescence is lighting up with an antibody called gamma H2X. And these are beacons for double strand breaks. So you can see now you have with the iron particles a column of these gamma H2X foci. So there's just a big pattern of double strand breaks all along the track of that iron particle, while the top one, which is at 2 gray of gamma rays, you can see just have a random distribution. So 2 gray is a pretty high dose, but here with the particles, it's just all or nothing. If you have a track, you get a column of damage. With gamma rays, if you went to a very low dose, you would have 0 or just 1 of these foci, those little dots. But at 2 gray, there's about 25 double strand breaks per gray, so you have on average 50 of these foci. So dose means something with gamma rays, but with particle tracks, it doesn't really have the same meaning. It's either the cell got hit or it didn't get hit. So this creates the problem that we don't have human data to know what happens to people when they're exposed to these radiations. There's a little bit of data now on cataracts in the astronauts. I'm a co-author, and it's something I was pivotal in bringing to the forefront was that you do see cataracts in the astronauts at very low dose, much lower than what the International Commission on Radiation Protection or the NCRP, the National Council on Radiation Protection and Measurements would be a dose where you would have cataracts. And the reason was they were using X-ray and gamma ray data and then trying to make a guess what would happen with particles. So even on a few shuttle missions, you'll see an excess of cataracts. So it's really about making that risk estimate that went wrong. And particles are just qualitatively and quantitatively different than ground-based radiation like X-rays or gamma rays. Now the terminology, people use the word ions, particles, nuclei. So they're not really ions because when you accelerate a particle to a few MeV, more than about 0.1, 0.2 times the speed of light, you lose all the electrons. You just have the nucleus of the particle left. So when we talk about the galactic cosmic rays, we're just talking about many different heavy particles. It's just a nucleus of atoms, oxygen, carbon, silicon, iron. We usually stop about silicon because it's very rare to have particles beyond. I mean, we usually stop at iron because beyond iron they're very rare. But the iron is a big peak, and peaks for some of the even charge, even neutron number. So that the ones I mentioned: carbon, neon, oxygen, silicon, calcium, iron. They're the big cosmic ray players. So they're going to produce unique damage to biomolecules. A lot of research on that. But how do you go from this understanding unique damage in cell models to predicting the risk in astronauts is a problem. And so no human data. You have to use animals or cell culture models to estimate risk and then try to predict what will happen to human. Shielding will have excessive costs for GCR. We'll talk about that a little bit today and more tomorrow about how much shielding is just. You could shield against the GCR. We're shielded down here on Earth by the atmosphere. It's about 1,000 centimeters of shielding. So 10 meters of water shielding shields you, but you really need to get about 3 meters before you really cut it down to a manageable enough. So even 1 meter is not enough. 3 meters or more, yeah, that's enough. So we say we can't shield it, we mean you need a lot of shielding, too much. A typical spacecraft shielding is about 0.1 to 0.2 meters thick when you average all the equipment and the walls of the spacecraft, and you can't do much better than that without really increasing the launch costs. And solar particle events is another one we'll talk about a little bit today, and then our speaker Nathan Schwaden from University of New Hampshire will talk about tomorrow. These can be shielded. This is a solved problem. But you might have heard otherwise. You might have heard that the solar particle events are the problem. That's because the space physicists have all these cool pictures of the sun blowing up and ejecting particles. But it's a solved problem because you can shield it. You need about 2 to 3 inches of water or polyethylene, and you get the dose down very low. I'll show an example of that. So what you need to know is a solar particle event started. So that can be done with dosimetry. And the dose rates never get that high. So when I say that, I mean you need to be able to get to shelter, get to shielding within an hour or two. And if you can do that, the risk is very small, less than 1%, much less than 1%. So it's not zero, but it's a very small risk. So it's really a solved problem, but people still talk about it because it's unpredictable when these events will occur. You don't know if it's going to occur tomorrow or next week. But you do know that there'll be 5 to 10 solar particle events per year. Most of them will be very small. The real risk is you're disrupting a mission because you don't know they're going to be small until a few hours after they started. And then most of them you can shield. Some of them you have to go to shielding. So as long as you have dosimetry and shielding available, you know how much shielding to project against all the solar particle events we've known so far. There is some chance that there'll be a bigger one in the future, but when you design something, you really can't design down to a zero probability. You have to be realistic about it, and you're in a game with all the other parts of a mission in radiation protection. You're going to design for radiation protection, but someone else has to be looking at rocket launch failures, mass allocation, volume allocation. So you're in this picture of radiation protection with a lot of other resources that engineers have to take into account. Okay, so the space safety requirements. So the astronauts, times have changed. They're really required to be under a certain acceptable level of risk. So it's not like Columbus where you just went out and really nobody knew what the risk was. They maybe say it was a high risk of scurvy or whatever, but now there's a limitation on how much risk NASA can allow the astronauts to have. And this has been debated for Space Shuttle and Space Station, but also for the preliminary plans for an exploration mission. So,
Frank, on that 3% fatal cancer risk, is that? Sorry.
Yeah.
On the 3% fatal cancer risk, is that what is that? A total lifetime risk of 3%, or is it a delta of 3% above the?
That's a good question. So it's actually an absolute risk, and you could calculate it the other way. So this is a quantity called READ, risk of exposure-induced death, but there's another quantity called excess lifetime risk. So that one's a little bit confusing. First, if you look in the epidemiology literature, it's an ill-defined quantity. And one of the things it doesn't do is that it doesn't take into account cancers that would occur, but the radiation moves them forward in time. So it's underestimating the risk. And it's also difficult at NASA because you're trying to compare this risk to other risks, not the radiation protection people, but they have to give information to flight directors or NASA management. And so it's better to give an absolute risk, and then that someone else can compare that to other risks that the astronauts or the mission we're taking. So we use an absolute risk of 3%, but it's lifetime.
I had earlier made a sort of a joke, I think before you got here, that if we selected astronauts that were chain smokers their whole lives, then we could forget about the radiation risk. And sort of that had come up because but
you'd have to take all those cigarettes.
Yeah, it's because the additional risk
of
in
fact,
cancer.
our new model takes into account smoking, that if you don't smoke, you can take more radiation. It's about a 30% more. So we're limiting things on an even playing field on risk, not on dose. So we calculate for gender specific, age specific at exposure. Now our new models also take into account whether you smoked or not, because there's a big interaction between smoking and radiation for like a half a pack a day, 10, 20 years, there's shown to be a big interaction between smoking and radiation, increase your lung cancer risk. But you're right, if someone smoked like 3 packs a day their whole life, the radiation doesn't really matter.
And so, yeah, but that actually, because I mean, how we got in this conversation was looking at the mass we'd have to add to meet the radiation requirement, whereas maybe just selecting an astronaut population that would otherwise be at risk, and the benefit of that.
Yeah. Well, NASA's able to do it because 90% of the astronauts are never smokers. They've never smoked in their lives. Less than 100 cigarettes is the definition.
So that factors in then if somebody came from Alaska and they're already exposed to a higher than average dose, or somebody starts out older and they have an accumulated dose. How is that adjusted?
Yeah. So we only allow to adjust for occupational exposures, so background radiation and it's a little bit tricky for the astronauts because there's a lot of medical diagnostic exposures, which are medical exposures from being an astronaut, but you're not supposed to take into account other medical exposures, and same with aviation. Some of the aviation exposures are taken into account, but not other ones, whether it's related to their work duties or not.
Someone's from Alaska and they're 50 years old, their chance of exceeding the limit would be higher than someone who's not.
I'm not sure about that. So usually it goes down a little bit with age. Risk goes down a little bit with age at exposure. From age 30 to 60, it goes down about 50%.
Because you're going to die of something else. I mean, you're going to die of natural causes.
Yeah, but it's like, again, it's an absolute risk. So if you do the calculation for someone 30, they can take only about 50% less exposure than someone 60, because that's part of the effect. There's also a little bit of age dependence on risk, like how many stem cells you have, or your sensitivity. Breast cancer, thyroid cancer are the two big examples that go way down. So when you're 20, you have a big risk from thyroid and breast cancer from radiation, but as you get to age 50 or older, it's a very small radiation risk. So some bump.
Basically is your best risk target in terms of
for cancer, but then the problem is you have other risks. So there's risks against first, and then we have the big problem. I mentioned that this is a different type of radiation. There's a large uncertainty. So NASA, as a safety factor, is looking at the 95% confidence level of the projection model. So that's something that they ultimately can waive, but that's part of the process, is to estimate the 95% confidence. But now there's other risks, and these are more new and emerging risks, and also ones that are probably more tied to heavy ions or heavy particles, which is a central nervous system risk, changes in cognition, Alzheimer's disease, and other diseases of the aging that seem to be caused by heavy particles in animal models. Again, very little data in humans. And then there's another one, heart disease risk. There's a new paper coming out, and this is just another one about a meta-analysis. It shows it's about 50% of the cancer risk is heart disease risk. So if you took the risk for a Mars mission, it's like 5%, not the 95%, but just a point estimate. The risk for heart disease death from radiation on a Mars mission is about 3%. So that's one we're just getting our hands on in a regulatory sense, what to do about that and what are the uncertainties there. But the central nervous system ones seem to go up with age. So it works against cancer, which is declining risk with age, but they're called degenerative risks. They seem to increase with age rather than go down with age and relative to exposure. And then we also have the acute radiation risks. These are the ones that are pretty much centered on solar particle events, and you have some probability. You don't accept any risk, but you have to have dosimetry forecasting and shielding in place. Flight rules like don't do an EVA if you don't have communications or comm. Don't do an EVA on the moon, extra vehicle activity, if you don't have a dosimeter that's giving you a readout. So if you put those flight rules in place, you really don't have a problem. If you would do an EVA on the moon without comm, without those real-time dosimetry, then you're kind of stupid because you could get a very large dose. But there's easy ways to avoid these things.
So Frank, the idea is to use dosimetry, identify when this event is happening, and then shelter down someplace?
Yeah, and you can shelter down.
Okay. But how quickly would you have to? And you have to figure this
It's
out.
on the order of 1 to 2 hours should be
Okay.
doable, and that's all you would need. 90% of the events, you have more than 24 hours warning, so you know the conditions are right. 10% of the events you have less warning, but it varies from like a few hours to the worst case 15 minutes. But then the ones you only have 15 minutes warning, it still takes a few hours to get a sizable dose. The dose rates are not instantaneous; they're over a few hours or a few days. Okay, so these requirements then set your shielding, dosimetry, and other requirements for the vehicle. So the SPEs, I mentioned you can shield. The GCR, we don't have good requirements now because so far there's not a good way to shield against them, and you're above the limit for a Mars mission or even a 1-year mission to an asteroid. You're above limits. And then finally, the last requirement is the ALARA requirement, or ALARA principle, that a low is reasonably achievable. And this is also complicated by uncertainties. How can a radiation protection person tell management or engineer how to do ALARA if you can't do the benefit side? I can tell you to do something and you might cost it out, but if I can't really tell you the benefits, it's not a very good calculation. So, so ALARA is as low as reasonably achievable. So this is a negotiation between radiation protection and medical personnel with managers and engineers on measures that you could take to get you even farther below a radiation limit. So the negotiation has to be based on what does it buy me to do something? Does it take me, if the limit's 3% and I have a mission that's 1%, I can tell you you can make the 1% a 0.5% if you do this. And then you have to cost that out whether it's worthwhile to do that. So you're below the acceptable level of risk, but you still have some other measures that could reduce the risk even further. And you're not required to do it at that point, but you're required to do ALARA and then negotiate what's the cost benefits of some measure. So it could be extra shielding, different timelines. We have one on the one example is on the space station and the space shuttle. We have a limit, a flight rule not to do EVAs when you're in the trapped radiation belts. So there's a window every day of about 10 to 12 hours where the vehicle's orbiting where you don't go through the Earth's radiation belts or Van Allen belts. So the flight rule is don't do EVAs then. And that's really ALARA because you could do EVAs then and you'd get some exposure, but you'd still be way below the limit. But it's just to avoid that extra exposure. Okay, so this is a very important problem. It's because we have these safety requirements, we're above the limits for a lot of the missions we like to take, and it's really about the uncertainties. I'll talk more about that. And then, so every review of NASA's exploration plans have this as the biggest factor for humans, and we're trying to challenge this. And really, it's the main focus now is about radiobiology research with simulated space radiation. Is the most cost-effective way to do this. And we have a facility in Long Island, New York, called the NASA Space Radiation Lab, NSRL, at Brookhaven National Labs. And there's a particle accelerator. I'll talk about that in a little bit, just to give you some background on what the NSRL is. You can simulate galactic cosmic radiation up to fairly high energies, not all the energies, but all the particle types, and then do simulation with experimental models, shielding models, dosimetry, to try and understand what's going on. Okay, and then I mentioned in terms of the safety limits, but also there's carcinogenesis, acute and late central nervous system risk. This is the one that we know the least about, but we see it in all these cell culture models of neurons, rats, mice. We see all these changes occurring, so it's something we're very concerned about. And then heart disease and cataracts. Cataracts are not really life-threatening. So we actually have a lens dose limit that we might drop. We're just trying to understand the problem better. So I don't think I have actually had a cataract replacement in my right eye. So I've never been in this space, but it's pretty common as you get older. I knew a famous ophthalmologist. He would end all his talks saying, "I hope you live to get cataracts," because if you, and sometimes everyone in the room has some. It's just which type. There's some types that are very minor. It just gets worse and worse as you get older. So that's like cortical cataracts. And then there's another type called posterior subcapsular cataracts, which are more related to radiation and other insults. And they're very bad because you lose your vision very quickly. So it depends on the type. But everyone gets some degree of cataracts. It's just a matter of how bad and which type. And then acute radiation risk is the other one we have. When these are ones where we don't accept the risk. So we have to have good measures to avoid that. And then the major problem is the uncertainties in the biology of these heavy particles or heavy nuclei. How much different are they really than X-rays and gamma rays? We can't use dose, or if we use fudge factors called the quality factor in dose, is that correct? And how inaccurate is it? Okay, so you'll hear more about this tomorrow, and I guess Jeff Hoffman talked about the environment. But I'll just remind you again. So the solar particle events, they're generally associated with coronal mass ejections. They're mostly protons, medium to high energy protons, up to a few hundred MeV. So, and then to remind you, like a shielding 100 MeV proton can penetrate about 9-10 centimeters of shielding. So when you talk about your body, the average depth of a critical organ is about 10 centimeters, and then the spacecraft, the wall thickness is only a few grams per centimeter squared. Everyone familiar with areal density units? We tend to use that a lot in radiation. So it's just the physical thickness times the density is the areal density. And we like to use that quantity because all the radiation properties scale with that parameter better, like the nuclear collisions, atomic slowing down of particles. But it also gives you a way to when you talk about different types of materials as radiation shields, it gives you a way to compare them on an equal mass basis. So you just have, like we say, aluminum, 10 grams of aluminum, 10 grams per centimeter squared. You divide by 2.7 by the density to get the physical difference. And water, it's 1. The density, polyethylene, about 0.95. And then you go to something like liquid hydrogen, which we'll talk about, and it has a very small density. So when we talk about 10 grams of liquid hydrogen, 10 grams per centimeter squared is a very big object to hold that because it's a very, very low density. So you need a big vessel to hold it. Okay, so the largest doses occur during solar maximum, but that's an 11-year solar cycle where each one's different, but it's kind of repetitive on a 11 years approximately length. But the solar particle events will occur throughout the solar cycle, except for maybe 2 or 3 years around solar min. You'll still have some probability of solar particle events. Then the trapped radiation, this is the Van Allen belts, or radiation belts is the inner belt with protons and outer belts with electrons. The Van Allen belts are displaced from the Earth's magnetic fields. They dip lower in the South Atlantic anomaly, SAA.
What is happening
Oh, so it's the sun's magnetic field and the solar wind's changing its intensity as
like the solar wind?
Yeah, so Nathan will talk about that in detail, but the solar wind is doing two things. One is when the intensity is up, it's blocking some of the lower energy cosmic rays from getting into the inner part of the heliosphere. But it's also a more chaotic magnetic field of the sun that is part of the phenomenon that leads to solar particle events. So solar max is when the sun's magnetic field and the solar wind is strongest, the galactic cosmic rays are least, and you have a higher probability of solar particle events. Solar min is when the magnetic field is weakest, and you have a higher intensity of galactic cosmic rays. So it's reversed in terms of GCR with the intensity, and it tracks with the solar particle events. Did anyone see? I guess the other day they think Voyager, Voyager 1 has now reached the end of the heliopause, and they can see the cosmic ray intensity going up even more. So I was quoted in a newspaper from Naples once saying E.T. can't come. So that's it. It was in Italian, but but it's really true because the GCR intensity just goes up and up as you go out, and then it's almost triple when you get outside the heliopause from what it is near Earth. So if you think about a long mission with this very high intensity of GCR, And I was on a couple papers like that about the probability of life coming from other stellar systems, and radiation was really the limiting factor for that. More than the ejection or the capture by our solar system was just how long it would take and how much the GCR would deplete any system. Even these radiodurans, which are like the most resistant species, they would be really depleted down to almost zero because of that long-term exposure to high-intensity GCR. But ET might have thought it's something else, like magnetic shielding or something. Magnetic shielding or something. Okay, and then the trap radiation is actually created from the cosmic rays and the solar particle events interacting with the Earth's magnetic field and atmosphere to create particles, and then they're trapped. And then the GCR, they're very high energy protons. They go out to at least 100 GeV, so this is way past 0.99, the speed of light. And they also have the Hz particles, Z for charge, E for energy, high charge and energy particles. They're not shielded, and they break up into other particles through nuclear interactions. And now, the contrast to the solar particle events, their abundances and energies are very well known. They vary over the 11-year solar cycle, but their makeup is fairly well known.
A quick question on the trapped radiation. Is it correct to visualize this as these are charged particles that came, for example, if they came from solar events, and some of these charged particles from the sun get deflected off in other directions, and some of them actually are trapped then in the Earth's magnetic field, and then they just go around a racetrack essentially in in the Van Allen belts?
Yeah, it's called the pitch angle distribution. They come from east and west direction.
Yeah.
And there's actually part of the source is actually neutrons that are produced in the atmosphere. And neutrons have a half-life of, I guess it's 7 minutes or 12 minutes. I should know that. But they decay into protons. So it's actually a lot of it starts off with the cosmic rays interacting with the atmosphere and making neutrons, and those neutrons decay into protons, and they get trapped in the magnetic field.
So a lot of the trapped particles in the Earth's magnetic field are secondary protons, not primary protons.
Yeah.
Is that
Some
right?
part of it, yes. Yeah.
Okay.
And their energies are medium energy. If the peak at very low energies, 1 to 10 MeV, but they go out to a few hundred MeV with an exponentially decreasing spectrum. So you can shield them. The space station is very well shielded from them. One of the interesting things about the Russian Mir space station was their crew quarters for the commander faced it either east or west. So his exposure was very high because the trapped radiation was coming in through his window. So you could see it in his dosimeter badge. But NASA has the space station is actually bulkier than the NASA Mir space station.
It's quite often in directional, is it not?
No, it's the trapped radiation. The protons are coming from the east or the west. They're called the magnetic pitch angle distribution. So electrons are different, but the protons are along the east to west. Yeah. But they can be shielded, and they do gotcha. So this is the GCR spectrum. You can see in terms of fluence is the number of particles per unit area. The protons dominate about almost 88% of the fluence, and then helium, and then you can see this odd even spectrum for the odd charge numbers are the highest fluence. But then if you weight it by the dose, so the dose is just the fluence times the rate of energy loss, or LET, dE by dx. You know, like the beta block formula or the Rutherford scattering formula, you remember that. LET, or stopping power, some people call it. And then if the dose equivalent is now taking that dose and weighting it by a fudge factor called the quality factor to predict the biological effectiveness of the particles. So when you weight it by the Q factor and the LET, you can see now the heavy particles are dominating the dose equivalent, which is the measure of the risk. So that's why we worry about the heavy particles more than the light particles, because even though there's fewer of them, they're more biologically damaging. And then this is another way to look at it about the range. The range is related to the 1 over the integral of the stopping power integrated over energy. And so you can see that if you look at the typical thicknesses as you go to and you map the range versus the LET, you can see spacesuit up to a mouse or a person or the atmosphere, which range of particles would be there and what their LETs. So we usually say that the particles between about 100 to 200 keV per micron are the most biologically damaging ones. And you can see which of these particles are there. So it's iron, argon, lower energy silicon will be the ones where the dominant RBE will be. And this is just dots, which ones we can simulate at NSRL or experimental facility. Okay, the other thing about this is LET is not the best predictor, so there's a little bit more of the details, but when you look at particles with the same LET but different charges, they have different track structures. So the track structures is talking about how the particle is depositing energy on the microscopic or nanoscopic scale. That's what where everything we're talking about biological effects is that you're actually damaging molecules. You're ionizing molecules, and that leads to DNA damage or oxidative stress, these kinds of things. So if you look at helium particles, their track structure is very narrow. It's all within about 100 nanometers from the particle's path. And then as you get up to these cosmic ray energies, a few hundred MeV per particle, you see that you have this strange track structure. So these little lines coming out are actually electrons that are ionized from water molecules in cells, say, and then those electrons are given a very high energy so they can go out and they can ionize more. So it's not only the particle path. In fact, what actually most of the biological damage is from these delta rays, these electrons that the particles produce. So what's interesting about this is the particle hardly touches anything because its track is much less than 1 nanometer, but the delta rays can go farther out. And when you think about gamma rays or X-rays, they also make delta rays, but they only make one at a time, except for when an electron, right before it stops, below about 100 eV electron, it can make what's called electron track end, where you can see 2 or 3 electrons being produced. But these heavy particles, very close to the track, it can produce thousands of electrons. So whatever is in the pathway of that particle is getting really ionized. And the other thing that's interesting is that a helium particle, it's got a high LET, but it's got a short range at this low energy, so it can't penetrate across a tissue. This is like this is the culprit in radon. Have you ever heard about the radon problem? That radon can cause lung cancer. So the radon gas gets embedded in your lungs and they emit alpha particles, but they only can go like a few cell layers. So they're very damaging, but the heavy particles from the cosmic rays, they can go right across your body because of their range, so that they can ionize along the whole track. So that's another thing. Is that bad, or how bad is it, is the question. Are we accounting for it by just taking a dose and multiplying by a fudge factor? Okay, and this is another way to look at it. So this would be an iron particle track near the peak energy of the cosmic ray iron spectrum, 600 MeV per nucleon. And then you can see across 10 microns and then close to the track, you can see what's called the core of the track. And you can see it's just going to be, whatever it hits is just going to be damaged very badly. Okay, the other thing that happens is nuclear reactions. As the particles go through shielding or tissue, they interact with the nuclei. So the atomic interactions with ionizations are occurring every few tens to hundreds of nanometers. The nuclear interactions are occurring on a very larger physical scale. So it's the mean free path is much larger. The average distance between a nuclear interaction is about 10 centimeters in water, or 10 grams per centimeter squared of aluminum for an iron particle. But when it does have a nuclear interaction, the amount of energy released is very large. So with atomic interactions releasing electrons, we're talking about a few hundreds of eV of energy being released, but having it occur quite often. But with nuclear interactions, we're talking about MeVs worth of energy is being released, and you're also making secondary particles. So this is where the neutron problem comes in, that if you have a cosmic ray interact with a material that has lots of neutrons, it can knock the neutrons out. So that's why we don't want to use lead or heavy materials in space, because they actually are more damaging than having no shielding, because they have this large number of neutrons that you can produce. Aluminum is sort of like in the borderline where you do get an important neutron component, but once you get a heavier than neutron, it gets really bad. And then as you go down to carbon or water molecules with oxygen, there's some neutrons being produced, but it's not as bad as lead or iron or steel, one of those materials. And then hydrogen is the best, because you're not making any neutrons per se. There's a very specific nuclear interaction called isobar resonances from particle physics, where you can excite a proton into a delta resonance, and then it decays as a neutron. But it's not going to happen that often. And there's not many neutrons will be produced that way. So we'll talk more about this tomorrow, about what's the best material. But right away, it's going to be hydrogen. You stop the particles more efficiently, and you make less secondary radiation, and you break up the particles. So the breakup, these nuclear reactions, is bad if it's in your body, but it's good if it's in the shielding, because that's one of the means to slow down and get rid of the radiation.
So, Frank, just maybe it's a visual. I have sort of a visual image of this, but I'm not sure it's really accurate or helpful. So, what you're saying is that when these projectiles, when these charged particles are generated in the first place, either ejected from the sun or by a supernova at some large distance, they get accelerated and they basically lose their electron cloud, right? The electron cloud is sort of left behind, and you just have the positively charged nucleus just racing through space in a straight line, more or less.
Yes.
And then, so it's arriving there, and then the job of shielding, well, I guess this is the passive shield, the difference between passive and active shielding, but fundamentally it sounds like you have two jobs to do. One is to slow down the particle, right, to decrease its momentum, and the other is to enrich it with electrons again, to try to recreate that electron cloud that it once had. Is it basically come down to these two things?
Yeah. So in the slowing down, it would get an electron cloud back. That's called like the effective charge starts to decrease as it slows down. But at that point, you're very close to stopping the particles. We don't worry about that too much. But the other part is so this target atom is the atom in the shielding. So when the projectile cosmic ray hits the aluminum atom, it's going to have a nuclear reaction, and you can see they have different characteristic particles being produced. You'll get a heavy fragment. Say it's iron. You have an iron nucleus. It hits an aluminum nucleus, and then what comes out can be anything. So you'll have a distribution of different new particles coming out. So it could be a calcium nucleus coming out. They'll still go along that straight line because they have a very high energy, and the change in momentum is small. So they'll come out, but it could be argons, silicon, oxygen, and then you'll have lots of light particles that come out with a bigger angular distribution. And then when the impact parameter, that B, is very small, then you might have total annihilation, where both the particles just totally annihilate each other. And you get lots of neutrons and protons and maybe some helium at that point. So that they're the two things. The slowing down, where that will occur, you'll capture electrons right before they stop. And then the other one is these nuclear interactions. And these kind of things are pretty straightforward. They depend on the material type, but they don't depend on things like molecular bonds or things like this, because the energies are well above the energies of molecular bonding or those things. It's really a matter of how many atoms you put in front of the radiation, and so that it goes through.
And Frank, and so you say hydrogen is the best as far as protecting for GCR. And different states of hydrogen, people are talking about liquid and also, am I correct in saying some people have even talking about solid?
You could. That would change the composition of how you place it, but just a matter of how many hydrogen atoms are there in the liquid state or the hydrogen. The chemical or the phase of the material doesn't matter. Just a matter. Because again, it's atomic collisions and nuclear collisions. There's no molecular collisions that come into play here. Okay, so this is what happens. You can see that. So a little bit confusing, but there's some of these curves are for solar particle events. So these ones that are very steep are solar particle events, and then the ones that are very shallow are cosmic rays. So this is through up to 35 grams per centimeter squared of different materials. So you can see, and this is without tissue and with tissue. So the liquid hydrogen is the best here. You can see for GCR it's coming down here, but when you put it on with the tissue, it brings it back up. So it's still much better than the other materials. But the difference between aluminum, graphite, or water as a shield for for GCR is very small, like an order of 10%. There's some gain there, but you can see also for the solar particle event curves, you can follow those. Any material does very good, but something with lots of hydrogen does the best. So liquid hydrogen, this is like the largest event we can think of in the last 40 or 50 years. And you can see it does a very good job shielding it with just 10 grams of material, any material, cut it down from a very high dose to a very small dose. And then you can use a lard to go past that thickness if you like, but certainly 10 grams. And then we say if you look at ones that might have been bigger, probably 20 grams of shielding. That's certainly doable, that you'd have a storm shelter with an average thickness of 20 grams. But the GCR, you've gone from maybe a 20% reduction, and it's just a shallow curve until you get out to about 2 meters. So.
But with hydrogen, don't you have a containment problem?
Yeah.
Prevent the boil off.
Yeah, so one of the things you might look at is, we're looking at liquid methane, because that has CH4, so it has 4 hydrogens for 1 carbon. And that's something that hasn't been vetted all the way, but that'd be a good one for that reason. And it's already a commonly used fuel, so if you could arrange a lot of liquid methane, that would be the next thing.
Because otherwise you're adding a lot of mass with the tankage.
Yeah, unless you can use the liquid hydrogen for your fuel. And if the Vasimir with Franklin Chang Diaz was working on that, was one of his ones he was considering, was liquid hydrogen. He was also considering helium, and helium wouldn't work as well because of it's really that Z to A ratio is the key driver. I'll talk about that tomorrow. So hydrogen Z to A is 1 over 1. And these other materials, quickly you get down to 0.5, and in some cases down to 0.4. And you want to be as close as the 1 as you can. Yeah, well, that would be the idea. Yeah.
So there are a lot of organic fuels which don't have those temperatures.
Mm-hmm.
You're right.
Yeah. So as long as they have good amount of hydrogen. Yeah. Okay, and then this is an example. I don't know if you know the MSL is going to land in early August, and they'll have the first radiation detection measurements on the surface of Mars. And so the Mars surface is interesting because you'll make a lot of the cosmic rays are coming through the atmosphere. They're breaking up. So I mentioned the mean free path is about 10 grams per centimeter squared. The Mars atmosphere is about 18. So you almost have 2 nuclear interactions on average. So you'll have a lot of particle fragmentation. And in that process, you make neutrons. And then the neutrons and the particles coming down will hit the soil. And depending on what kind of soil that is, you'll get neutrons and protons going back up. You have a downward flux and an upward flux, and that's the same in the atmosphere here on Earth. It's called the albedo component. But now this is a prediction that the albedo component will depend on which material the soil is made out of, whether it has a permafrost or a Martian regolith, which has a lot of silicon and some iron in it. So you'll make more neutrons from those materials than the permafrost would. And then John Wilson, who's retired now, but one of my old mentors, he had a prediction about the temperature dependence of the neutron field, that you would have less neutrons in the winter because you'd have more frost covering up the regolith than you would in the summer. And I guess someone else mentioned there also could be a problem of the thermal neutrons escaping if the temperatures weren't too high, but I'm not too sure about that. But whether they would not escape, some of them might go up and then come back down if they're very low energy and the temperatures are too low.
This curve,
Yeah, it's a little blurry.
the curve that you're showing on the right is a prediction of
Yeah.
what you think it's going to be, and
Yeah.
so the MSL measurements are going to
Yeah.
confirm or refine that decay
Yeah.
curve.
Yeah.
Is that right?
Yeah, and then so a couple other points. So the bottom curve is the downward or forward flux of neutrons, and then you can see the other ones are the prediction. So at very high energies, the forward flux is dominating. Then below about 100 MeV, the upward flux is starting to dominate. And so that depends on which type of soil you're on to see how many neutrons you produce. And that's pretty well known. That's how they discovered water on Mars, is by looking at the neutron and gamma rays coming up and saying that if it was this type of material, you'd have this characteristic neutron and gamma ray signature versus another. Right? And the other thing, since I'm on this chart still, the other point is that on the moon you don't have the neutron issue nearly as bad because you haven't cut down the cosmic rays, so it's a relative thing. So I mentioned 2 mean-free paths and this shielding, so you've cut down the primaries somewhat. So this backward neutrons component, relatively speaking, is going to be, it could be 1/3 of the risk. But on the moon, you haven't cut anything down. So when it hits the regolith, the primaries are still there big time. So you might have some neutrons come off the lunar surface, but relatively speaking, it's going to be less than 10% of the risk. The prediction is about 5%. But on Mars, it could be about 1/3 of the risk is that upper neutron component. And it's not just neutrons, there'll be charged particles coming up too. Okay, and then the other thing is the dose rates in space. So this is a prediction versus calendar year. You can see the solar cycle effect that if you look at these yellow ones here. Okay, yeah, you can see this is the solar cycle. So this is solar minima around 1996. These are the Hubble flights coming up, or others, high altitude flights. And you can see it coming down, and this was a solar minimum was occurring in 1977. So we missed that one, but you can see these are the Apollo missions. So the dose rates can be very low. So these would be low altitude old shuttle flights. These are also about the same altitude but a higher inclination. These are the shuttle Mir and space station type missions, so it's a higher inclination, 51 to 6 degrees typically, and also NASA used to fly 57-degree missions for DoD. And they were, so you see the solar cycle here, and then these ones are not cosmic ray dominated. These ones are trapped radiation dominated, so they're just very high altitude missions. This group here, and then, but you can see this one would be the Mars type exposures going to Mars. You'd be getting on this order of 1 to 2 millisieverts per day. So that's not a very high dose, but if you have to go for 1,000 days, it builds up with time. So the limitation becomes how long you have to stay in this exposure. The lower inclinations, you have, so there's 2 effects going on. The GCR doesn't really depend too much on the altitude, just a few percent. But the trap radiation has a big variation as you go down below like 380 kilometers. It gets to be very small. Yeah, and an inclination is changing the GCR and the trap. So the GCR doubles from 28 degrees to 51 degrees. So a lot of the early space shuttle missions were 28 degrees. That's like the longitude of Florida is 28 degrees, and where they launch in Russia is 51 degrees. So
right. I was just when you went up to 51.6 on station, it was actually better from a radiation standpoint.
It's worse, I think. It's better from the it's better from the trap point of view, but worse from the GCR point of view. Yeah. Okay, so we're really limiting our time. So if you want to go on the space station more than a year, this becomes a problem, and the space station is vulnerable to when you can change the crew out. So everyone can take one or two missions on the space station, but even as you go past 1 year, these confidence intervals become a problem for female crew or somebody who's flown before.
What about somebody like Sergei Krikalev, that total time in space is over 2 years?
Oh, yeah, I have that on my computer. Yeah, it depends on.
Is he one of those dots on those points on your?
Yeah, well, it is at the NASA, but I have his exposures. I can show that tomorrow.
Okay.
Well, Polyakov also on the single duration.
Yeah.
No, I'm talking cumulative.
Yeah,
he was over 2 years right there.
Yeah. Yeah, some of it depends on if you're at Solar Max or Solar Min, and also, I think in a couple cases they did have people that wouldn't be approved in our system. Probably 2 people in the Russian cosmonauts.
How much difference is there between the standards that the cosmonauts are using versus NASA astronauts?
We have an agreement. In fact, that was one of my older jobs, was to make the agreement with the Russians. We agreed to the 30-day and short-term dose limits, and we agreed to disagree about the career limits. So we have this 3% risk. We're using an ICRP standard where everyone gets 1 sievert. So you're allowed 1 sievert over your career. So these fellows were up about 0.3 sieverts. So in terms of the ICRP standard, they were okay. And but how they account for dose rate and radiation quality is also different. And what the meaning of that 1 sievert in terms of risk is kind of vague. So we think risk is the true thing. All these things like sieverts and millisieverts, don't listen to those radiation people. These are just made up quantities that don't have any meaning. If I was going to start from scratch, I would never use these quantities and just teach everybody in risk and say this is your risk. 1 in 100, 1 in 1,000, not 7 millisieverts. These are like old quantities that are very inaccurate. So it's better to, in my opinion, it's better to give people risk predictions with confidence intervals rather than tell them dose, because most people, unless you're trained in it, wouldn't know what 8 millisieverts versus 7 sieverts, these kind of things.
Is there a large enough sampling though to determine risk?
Well, but it doesn't matter. That's what you have to do. So you have to give the best system, put it together, and make the estimate. So we use atomic bomb survivors and other people exposed as a starting point. And then as you go to the longer missions, NASA's planning like the asteroid rendezvous missions. They're very hard to find ones that take less than a year, so they're 1 year or greater. To visit the Mars moons where you just need one launch system. You go there and come back, so it's very cheap compared to going to the moon. We have to have several major systems. So that's one of the motivations for people talking about those type of missions is the fiscal hurdles are smaller when you just go and come back. And then the Mars mission, 900 to 1,100 days. So these missions, that continuous dose rate over a couple of years is what gets you. Okay, so the uncertainties are the major ones. I hope I conveyed you. There's a quality factor, but there's also about dose rate. That one of the big fudge factors we use is the atomic bomb survivors or acute gamma ray exposures. What about someone who's exposed chronically? And it's sort of like the stock market. It used to divide by 2.5, then 2. Now they're dividing by 1.5. So they're just guesses, and they're rounded off numbers. I think it's 2 times lower. Some committee says. They used to say it was 2.5 times lower. Now the most recent one from the Academy of Sciences is 1.5 times lower. So there's a lot of uncertainty there. So you're dividing by that number, and if you go from 2 to 1.5, you've increased your risk estimate by 33%. So it's a big deal if you're constrained by these limitations. And then there's also the how do you use experimental data to predict risk in humans, and then individual factors are a big deal. Okay, so these are some predictions for 1 year in space now. You can see they depend on the person. So a new model that I helped develop that NASA looks like they're going to prove is to look at smoking effects on radiation risk. So it's mostly lung cancer, but there's a lot of cancers that are attributable to smoking: colon cancer, leukemia, stomach cancer, etc. And if you adjust people's background to take into account that they never smoked, and keep in mind that the way you calculate radiation risk is your radiation risks are proportional to your background in the predominant manner. That's called the multiplicative risk model. So if you have a lower background, your risk goes down, and you can see that it's about a 30% drop. In some cases for females, 20-some% for males, and so these would be for 1 year. So that NASA not only looks at the point estimate, so the 30-year-old male has a 2.26. If I use the average U.S. population, but his 95% confidence level is 8.1. So I want to keep that upper 95% confidence level below 3, so that these numbers are a problem until I lower the risk level, the uncertainties down to get it to a much smaller uncertainty. So this is like more than a 3-fold uncertainty.
Just out of curiosity, on the females, what percent of that is breast cancer risk?
It's a little bit breast and a little bit ovarian cancer, but what's surprising is a lot of it's lung cancer that the models from atomic bomb survivors and Hiroshima can predict a much higher absolute risk of radiation-induced lung cancer for females than they do for males. And that's a big part of it. There's also a little bit of effect because they live longer. Females, so they on average are living like 4 or 5 years longer, and it's a lifetime risk calculation, so you get a little bit bump up just because you live longer. And I know some female astronauts told me they complained about, like Bonnie Dunbar always would complain, why Alan Baker, why should I be penalized because I live longer? But that's the calculation.
So
Then you
Frank,
can argue, do I negate if you die at 88 from radiation compared to 78? How could you make that argument?
so these are percentages or multipliers?
These are percentages. So it says like a 1 year in deep space, a 30-year-old male would have a 2.26% absolute risk of dying from his radiation exposure.
As opposed to a 1.79% risk if that 30-year-old was a non-smoker living on Earth all the time.
I know if he went into space and took the exposure.
Right, if he went into space and took the exposure, his risk would be, on an absolute level, 2.26%. But if he just stayed on Earth as a non-smoker, it would be 1.79.
Oh, no.
So that,
These are just saying if I just, so you have to do these as population-based calculations. So we're using one model, it's an older model that the NCRP said was to use the U.S. average population for the astronauts. So this most recent work we did was say, well, that's not really appropriate because the astronauts are healthier. There's a well-known healthy worker effect, and the major part is the smoking effects, because smoking even today causes more than 20% of deaths from all diseases in adults. So this is saying my model population is a population of never smokers, and their radiation risk is less.
So just, the Russians, of course, have been very hesitant to fly women for a lot of different reasons. And they certainly, like on their Mars 500 and a lot of stuff they do in radiation, it's purely male cohorts. And so these numbers would say, based on the NASA standards, that most of your female population is not going to meet the 3% and the men are. So do you think this will have a negative impact on?
Yeah, so this is what we've been using at NASA for a long time, and then so it's, again, it's based on risk. So neither one of them really meets it, and the problem is the uncertainties. How do you drive that uncertainty down? It could be that you're closer to the lower number, right? If I just had a narrow uncertainty, maybe I'm closer to this number. So from a safety point of view, you look at the high end, but from a scientific point of view, maybe the true answer is on the low end. So you just don't know until you narrow the uncertainties, is the question. So, okay, and then if you convert this into how many days in deep space you could take and have a 95% confidence to be below the cancer limit, you can see it's coming in. See, it got worse. The first thing you notice is it got worse. In the older models, there was a very strong age dependence, but the new information about dose rate and some other details about epidemiology made the problem worse. But you can see, so it's about, the best case is about 200 days, and one thing that's misleading is this is solar min. So the solar min is only 1 or 2 years of the solar cycle. If you go to solar max, it's about double these numbers. So it depends on where you go as well. Okay, so we argue. I'll try to end now because I'm at the hours. That lowering the uncertainties is the way to go. If you could lower the uncertainties twofold, and this is an example, you could pretty much double your time and space. So when you say that, there's a caveat, because if you lower the uncertainties, the point estimate could also move up or move down. You don't know. So a narrowed uncertainty distribution, you don't know if it's going to narrow where you were or narrow higher or lower, but we still think we want to know that. And so this is very, very inexpensive to do it this way. We think like one grant is worth about 1 pound of shielding. That's my analogy. So and you need, like, just for the solar particle engine, you need about 1,000 pounds of shielding for a few man crew, and then for GCR you need tons of shielding. So the question would be is, can you have 1,000 grants solve the uncertainty problem? And if you could, that would be a good investment compared to trying to adding a. So. Okay, and then all I know here, so I put this together. What's going to solve the problem? So we think we're on the right path to reduce the uncertainty. We think we can go from our uncertainty now of about a threefold, so that's a little bit more than 3 times the point estimate, to at least a twofold, probably better within this decade, next 7 or 8 years. And we've scoped out shielding for years and years. We think the best you could do with optimization and materials at about a 15% reduction. Crew selection, we did a few things already, and there's some other things in the works that you probably get a 50% reduction. Biological mitigators, based on what's been done in the past with low LAT, gamma rays, X-rays, we don't think you can do more than 30%. That's really a kind of a stretch to say you get 30% because of the complicated types of radiation. But all of these would be clouded by the uncertainty. So you can say 15% shielding, but it's the same thing. I need to know the uncertainty because I can't bank on it until I know. You can't give someone a number without giving the error bars on your estimate. And so the uncertainty is still the driver for us. So we get it down to less than twofold, I think.
How do you screen for sensitivity?
Yeah, so you learn from the experimental models, but like which pathways, what's the biochemistry, which are the genes that are conferring resistance and sensitivity. So you learn that from experimental models, and if you can get that all vetted and validated, then you should be able to look at humans.
So you look at their DNA and profile of an proposed astronaut, or what?
Yeah, you can look at specific genes, like how they're expressed or overexpressed or underexpressed. Also, there's certain types of biological tests that you would know if, like a pathway, because in biology it's kind of complicated. If you know about pathways that are dominant, and then there's major players in that gene pathway, so it's not just one gene. So there's tests along those lines that are being developed.
You look at family cancer history.
Yeah, you can, but what you do with the information is a little bit fleeting at this point. There's some big players, but there's a lot of things like you can't put a number on it. To get to the punchline, if I look at your family history and saw C, D, and E, I say, well, could be something there, but if I can't put a number on it, I can't really go anywhere with that information at this point. So we need to know more. Yeah.
Is ethnicity a factor?
Which one?
Different populations of people that would be better to go into space than others?
What was
I mean,
the
if you're
first
looking at genes, ethnicity.
Not that I know of. No.
No.
There's a few syndromes. Yeah.
Yeah, I don't know. It was just since we were looking at genes.
Yeah.
What drugs can affect radiation, or can I noticed you said
to
drug
reduce
testing
risk?
there. Yeah, can reduce your risk.
Yeah, the people always talk about antioxidants, and then the newer one, we're funding a couple of studies as drugs that are not only antioxidants but anti-inflammatories. They seem to work in models, but it really hasn't been proven. But that's the kind of direction you would go in. And then there's also things with there's a new thing called microRNAs or overexpressing DNA repair proteins. There's a lot of ideas that are early, like low TRL ideas that seem to work in experimental models, but it really hasn't been developed how you would use it in a human. Except for anti-inflammatories, that could be done now. Just the importance of it hasn't been vetted out.
So like taking ibuprofen and a leave
Yeah.
while you're in space.
Yeah, and it's also whether it will work in a very healthy person is a question mark. Some of these studies show these vitamins work in sickly people. Then you give this to someone who's already healthy, it actually can work against you. So there's a lot of things that are not known there.
And Frank, we know this from the testing we do with animals. Is that how you get this information with the antioxidants, or is there some other way of modeling?
Yeah, there's a lot of things about DNA damage and repair and oxidative stress in tissue and cellular systems that have been looked at. So
it's all from animal studies?
Yeah, animals and cells, yeah.
What about got a proposal from the Russians looking at the use of light water as for radiation protection, make the cosmonauts drink light water, like as opposed to heavy water. Have you heard anything about that?
No, I haven't heard that one. So.
You know, they're very superstitious.
Yeah. That's why so I think crew selection is the key one, and understand how to make the selection. The mitigators. The problem is a lot of these mitigators. If you really knew how to do that, you would have a cure for cancer. I think that's my analogy, because they're really talking about things that can prevent a cancer, So if you really knew how to do that, it would work outside the arena of radiation. And nobody can do that. So it's really a stretch when you think about it. Yeah.
I recently heard a lecture on anti-angiogenesis drugs, so drugs that prohibit the growth of blood vessels. And the idea was, I think it's William Lee, a researcher who was working on that, and I think the idea was that there are a lot of cells that have the potential to become cancerous after the abnormal cell size reaches above 0.1 millimeters cubed. But if you prohibit blood vessel growth to those tumors with drugs, you can likely decrease the chance of those small tumors becoming cancerous and metastatic. So I don't know.
Yeah, actually, our speaker tomorrow, Lynn Lackey, is a protege of Judah Folkman, who's discovered angiogenesis' importance in cancer. So she'll probably talk a little bit about that. So their idea is that actually that most people have malignant cells, and it's just a matter of whether the cells are going to progress to become a tumor or not. So that if you think about cancer that way, that you already have cancer in some sense, it's just a matter, is it going to progress into a tumor? So if you understand that, you can use a different way to attack the problem. So Lynn will probably talk a little bit about that tomorrow. Yeah.
Quick question. So I'm not. I guess I don't understand why reducing the uncertainty will help you, because isn't there a chance that once you quantify it more and reduce the uncertainty, it pushes you towards the wrong end of the spectrum in terms of the.
Yeah, there's a chance there, but I would still think it would go the other way.
It'd be nice to.
Yeah.
So, engineers would typically take the conservative estimate on that end, but are the numbers such that they're so sensitive at varying or even just narrowing that upper bound on the uncertainty would buy you a lot more in terms of the engineering development, say, for example, the shielding required?
So you're agreeing or disagreeing?
No, I'm asking you, are the numbers that sensitive?
Oh yeah,
that reducing that uncertainty in any manner, even if it pushes you up, is of value.
The background is this: is that like an engineer, and you can do a test and do it very quickly, but with these kind of studies, you have to irradiate mice, and you do mechanistic cell models and biochemistry, but you also have to have a key component with a mouse study, and so I didn't mention, but the so NASA, I have a minute. So we created this NASA Space Radiation Lab. It was actually discussed in 1958 when NASA was created, but we opened it in 2003. So this is the NASA Space Radiation Lab. You see the big RIC collider, the big ring in the top. That's related to Big Bang science with very high energy particles. And so you shoot the particles, and we have this little lab, and the mice get zapped. So but the thing is, so you're thinking of engineering, you can do a test and then you retest and retest. With one of these experiments, it's like 6 years turnaround, because it takes like 1 year to procure the grant, 1 year for a colony of mice to be irradiated, and then you have to wait 3 to 4 years before the results are in, and then another year to publish. So we're like on our second test. So the problem is, no one would know this without having some inside information. Is we don't have the critical studies done. And I'll give you an example. When we opened this, I went out of my way to make sure we had a big study on leukemia. And we went and did that study, and leukemia risk was being way overestimated. We found that it was being overestimated, at least by a factor of 4.
Okay.
So from heavy ions, that we were way overestimating. So the thing is, what you're saying is true, but we don't even have the critical data in yet.
Okay.
And because of the nature of these types of studies, you have to have like 3 or 4 rounds of these mouse studies. So there'll be another 10 years before we have all the data and to say, did you do this study, this study, this study? You can't say you're not going to reduce the uncertainties until you have some suite of studies that are behind you.
But
we're not even there yet. So.
The common consensus is that with more validation, the bounds will reduce towards the average more so than being skewed towards the upper end of that.
Yeah, I would guess there'd be an overestimated.
You're overestimated. That's the common consensus.
Yeah.
Okay.
But you got to prove it.
Right. Yeah, that's what I was asking, basically.
And then we haven't done the right studies yet. It's just hopefully we're going to get them done in the next decade.
I think there's another big correlation cost benefit. One aspect, of course, you're just correlating with risk, but the other is that there's enormous correlation between radiation shielding and mass. And that's a huge cost. And you've got to launch this stuff. So if you can reduce uncertainty, potentially reduce mass, of course, or you may have a material solution, whether you use
the methane or whether you use other hydrogen intensive materials. But if we can reduce mass and risk, then it seems like it bolsters your argument for more studies that narrow that zone.
I agree. Yeah. Okay.
All right. Thank you, Frank.